Let's keep talking about vectors. So right now we're going to introduce components, and components are to vectors what coordinates are to points when we represent them in space, a plane or in space. So a vector we can consider to be in the plane. Here it's in the xy plane. And any vector is equivalent to, in the sense of having equal magnitude and equal direction, to exactly one vector that starts at the origin. And that one is going to be called a position vector. That's what this is called. Not a term I'm going to use a ton, but whatever. So here I've drawn the vector A, and it starts at the origin. That's its initial point, and its terminal point is at the point A1, A2. Well, this point A1, A2, this terminal point is uniquely determined by the initial point being at the origin. So these points A1, A2 serve, or this coordinate, these coordinates A1, A2 serve to uniquely identify this vector. So we call those the components of the vector. So A is equal to A1, A2. To distinguish that I'm thinking about this as a vector and not a point in the plane, I put these brackets about it like that. All right. Similarly, in 3 dimensions, x, y, z, I can take any vector and I can have the initial point be at the origin. The terminal point then has some uniquely determined coordinates, a1, a2, a3. So I can always talk about this vector A as having coordinates, components, a1, a2, a3. And again, I use the brackets. Just like with coordinates, these are ordered pairs or triples. The order that you do it, that you write them in, matters. And just like with coordinates, we can call this the x component, the y component, x component, y component, z component. Okay, so what if we start with a vector that does not have initial point at the origin? Well, it's actually fairly simple to find the components so long as we have the initial and terminal point. So if the initial point is x1, y1, z1, the terminal point is x2, y2, z2, then the components of the vector v are just given by the differences of the coordinates. Specifically, the terminal point the terminal coordinates minus the initial coordinates. So x2 minus x1 is the x component, y2 minus y1 is the y component, z2 minus z1 is the z component. So really, this is just saying what is the change in each of the coordinates, because that's what a vector cares about. We started here, we're over here now. How did each of these components change? These coordinates change? Those are the components of the vector. So for example, let's take this vector v right here. It starts in the xz plane with the way I've drawn it, 2, 0, 4, and then it ends in the yz plane the way I've drawn it, 0, 2, 1. So the components are going to be the terminal components minus the initial components. 0 minus 2 gives me negative 2. 2 minus 0 gives me 2. And 1 minus 4 gives me negative 3. So this vector has components negative 2, 2, negative 3. That means that it's changed by negative 2 in the x direction, 2 in the y direction, negative 3 in the z direction. So here's question 1. I'm going to ask you to turn this last idea a little bit on its head. Instead of starting with coordinates of initial and terminal points and finding components, we're starting with a vector. In this case, I'm just dealing with x and y. We're in the xy plane. A vector with components 1 and 3. So v has these for its components, and we're considering a representation with initial point negative 1, comma 2. What is the terminal point? Remember, we obtain 1 and 3 by taking the coordinates of the terminal point and subtracting the coordinates of the initial point. So what do we have to do with the components and the coordinates of the initial point to get back to the terminal point? And I suppose another hint, this is where we start, this is how things change, where do we end up? I originally defined a vector as a quantity that has a magnitude and a direction, but I didn't really define what magnitude or direction mean. Well, now that we have a real coordinate-based way of talking about vectors, we can actually define what the magnitude is. So the magnitude or length of a vector A is really just the length of any representation of the vector. So take any representation, any initial and terminal point that gives you a particular vector, and just take its length. So in 2 dimensions, first of all, we can always get the length in terms of the components of the vector. We don't have to talk about the coordinates of a particular representation. We usually just look at the components. In 2 dimensions, we're just looking for the length of a line segment starting at the origin, going to some point, and we know that the distance from the origin of a point is the square root of the sum of the squares of its coordinate. This is just the Pythagorean theorem. So from 2 dimensions, we get that I'm always going to write, if I have a vector A, A1 and A2 will always represent its components. So the vector A's length is the square root of A1 squared plus A2 squared. 3 dimensions, it's really not that much different. We get that the length or magnitude of A is the square root of A1 squared plus A2 squared plus A3 squared. Where does this come from? This comes from basically applying the Pythagorean theorem twice. If you'd like to see it, I'd be more than happy to show you in class, but I'm not going to do it up here. Just note that this really looks very, very similar to what we have going on up here. Now we can combine this fact about the magnitude of a 3-dimensional vector with the fact that if I have 2 points in 3-dimensional space, then the difference of their components, of their coordinates, gives me the component of the displacement vector between them. This gives us the length of, or the distance really, between any 2 points in 3-dimensional space. So the distance from x1, y1, z1 to x2, y2, z2 is really just the length of the displacement vector from this point to this point. The components are x2 minus x1, y2 minus y1, z2 minus z1. And so the length of the vector is the distance between them, which is the square root of the square of x2 minus x1 plus the square of y2 minus y1 plus the square of z2 minus z1. This looks a lot like the regular old distance formula for 2 dimensions. In 2 dimensions, it looks like this. We just get rid of the z components. Here, we just throw that in. Great. So what is the distance between, say, the point 3, 1, negative 2, and the point 5, negative 5, 1? Well, this formula says let's take the square root of 5 minus 3 squared plus negative 5 minus 1 squared plus 1 minus negative 2 squared. This simplifies to be the square root of 2 squared plus 6 squared plus 3 squared. This is really negative 6 squared, but whatever, same thing. Now, in fact, let me write that as negative 6 squared. So 2, negative 6, 3, we should now be recognizing as the components of the displacement vector from this point to this point. Okay, well, I do the math. 4 plus 36 plus 9 is 49, take square roots, and I get 7. That's how long that is.